On January 27, 2026, researchers at MIT released something unprecedented in the history of interstellar astronomy. Not a single image, not a series of snapshots, but a continuous 28-hour video sequence showing interstellar comet 3I/Atlas moving against the background stars. This footage, compiled from data captured by NASA's Transiting Exoplanet Survey satellite between January 15 and 22, represents the first time humanity has watched an interstellar visitor in motion across multiple days. You can see the comet as a distinct bright point, dragging a faint tail through a dense star field, growing dimmer as it races away from us at magnitude 1.5, roughly 100 times fainter than what the naked eye can detect under perfect dark sky conditions. But buried in that same MIT analysis was a discovery that changed the timeline of this entire story. When researchers examined TESS's archival data from months earlier, they found something extraordinary. The satellite had accidentally photographed 3I/Atlas in May 2025, a full 2 months before astronomers officially discovered and identified it as an interstellar object. The machine saw it before we did. By carefully stacking over 9,000 individual images from that pre-discovery period, the team reconstructed the comet's inbound trajectory through actual photographic evidence rather than mathematical back calculations. We now have visual proof of where this visitor came from and how it evolved as it approached the sun. In this video, we will explain how multiple space telescopes have combined their observations to build the most complete picture yet of an interstellar visitor. What the unexpected chemistry and behavior of 3I/Atlas tells us about conditions in alien solar systems, and why the upcoming Jupiter encounter could provide our final close look at this mysterious object. Let's get started. The Transiting Exoplanet Survey satellite wasn't designed to study comets. Launched in April 2018, TESS exists to find planets orbiting other stars by watching for the tiny dips in brightness that occur when a planet crosses in front of its host star. To do this, TESS stares at large patches of sky for 27 days at a time, taking images every 2 minutes and building up massive archives of how stars change over time. This continuous monitoring makes TESS incredibly valuable for time-domain astronomy, the study of objects that change on timescales of hours to weeks. When 3I/Atlas was officially discovered in July 2025 from ground-based telescopes, astronomers immediately recognized they had a problem. The comet was moving fast, as all interstellar visitors do, with only a limited window for detailed observations before it would fade beyond the reach of our instruments. Every telescope had its strengths. Hubble could measure the nucleus size precisely. JWST could analyze the chemical composition through spectroscopy. But none of them could provide continuous coverage showing how the comet behaved hour by hour over multiple days. That's where TESS became unexpectedly crucial. The 28-hour video sequence from January 2026 captures 3I/Atlas at a distance of approximately 2.4 astronomical units from Earth, already well past its closest approach to the Sun and heading back into interstellar space. The footage shows exactly what you'd expect from a comet, a bright central condensation surrounded by a coma of gas and dust, with a tail stretching behind as solar radiation pushes material away from the nucleus. But it's the continuous nature of the observation that makes this valuable. Instead of discrete snapshots separated by hours or days, scientists can watch the comet's brightness and tail structure change in real time. The most important finding from this sequence is the confirmation of 3I/Atlas's rotation period. By measuring how the comet's brightness varies over time, researchers determined the nucleus completes one full rotation every 7.1 hours. This is relatively fast for an object of this size. The brightness variations follow a regular repeating pattern, which tells us the nucleus is probably elongated or irregular in shape, presenting different surface areas to the Sun as it spins. More importantly, this rotation rate is close to the theoretical limit for a loose pile of rubble held together only by gravity. Spin much faster than this, and centrifugal force would start flinging material into space. The fact that 3I/Atlas maintains this rapid rotation without flying apart suggests the nucleus has significant internal strength. It's a solid, or at least well-consolidated body, rather than a fragile aggregate of loosely bound pieces. The tail behavior in the TESS video adds another layer to this picture. Even at 2.4 astronomical units from the Sun, more than twice Earth's distance, the comet continues to show active dust production. This is somewhat unusual. Most comets quiet down significantly as they move away from the sun and cooling takes over. But 3I/Atlas maintains a complex tail structure with visible variations that sync with the 7.1-hour rotation period. This periodic wobbling in the tail suggests different areas of the nucleus are more or less active as they rotate into and out of sunlight. It's the kind of detail you can only catch with continuous observations. But the real surprise came when MIT's Daniel Mutrishna decided to search TESS's complete archive for any earlier glimpses of the comet. Standard practice in astronomy is to look backward through old data whenever something interesting is discovered. Often the object was there all along, just too faint or unremarkable to catch anyone's attention at the time. In this case, the archive search turned up thousands of images from May 2025, showing a faint point of light on exactly the trajectory that 3I/Atlas would later follow. At that time, the comet was still approaching the sun, much fainter and less active than it would become. Individual images were too noisy to be useful, but by stacking over 9,000 frames together, essentially averaging out the noise, while preserving the real signal, researchers recovered a clear detection. This pre-discovery imaging is scientifically valuable for several reasons. First, it extends our observational baseline. We can now trace the comet's path, not just from July 2025 when it was officially found, but from May, giving us a longer arc to work with when calculating its precise orbit and origin point. Second, it allows direct comparison of the comet's appearance and activity level across an 8-month span. The May 2025 version, captured while still approaching the sun, looks noticeably different from the January 2026 version heading outward. The evolution of the coma, the changes in brightness, and the development of the tail all provide clues about how solar heating affects an interstellar object's structure and composition. What makes this detection particularly interesting is the question it raises about how many similar objects we've missed. 3I/Atlas was only recovered in the May 2025 data because researchers knew exactly where to look and had the sophisticated processing tools to extract a faint signal from noisy images. If this comet had been slightly less active, or if its trajectory hadn't happened to cross TESS's field of view at the right time, we might never have known it passed through. The implication is sobering. For every interstellar visitor we detect, there are likely many more that remain invisible, either because they're inactive and dark, or because they pass through regions of the sky we're not monitoring continuously. While TESS provided the motion picture, the Hubble Space Telescope delivered the crucial measurement of the comet's actual size. This is harder than it sounds. When you observe a comet through a telescope, what you see is the bright coma, the cloud of gas and dust surrounding the nucleus. The nucleus itself, the actual solid body, is buried inside that glowing envelope. Extracting its size requires careful photometry and modeling to separate the light from the nucleus from the much brighter contribution of the coma. Hubble accomplished this through high-resolution imaging that resolved structure within the coma and allowed researchers to identify the central point source. The result is striking. 3I/Atlas has a nucleus approximately 2.6 kilometers in diameter with an uncertainty of about 0.4 kilometers, depending on assumptions about its surface reflectivity. To put this in context, that's 40 times more massive than 2I/Borisov, the interstellar comet that visited in 2019 and had a nucleus only 0.7 kilometers across. Compared to Oumuamua, the first interstellar visitor we detected, which was probably less than 200 meters long, 3I/Atlas is at least 20,000 times more massive. We're looking at a completely different class of object, not a pebble or boulder, but a small mountain drifting through space. This mass measurement matters because it connects to other observations in ways that validate the overall picture. When astronomers track 3I/Atlas's path, they find it doesn't follow a perfect gravitational trajectory. The comet shows non-gravitational acceleration, small deviations from where it should be based purely on the sun's and planets' gravity. This acceleration comes from the rocket effect. As the nucleus heats up and ice sublimates into gas, that gas jets away from the surface, pushing the nucleus in the opposite direction. The magnitude of this push depends on how much gas is being produced and how massive the nucleus is. A small object gets pushed more easily than a large one. The Hubble size measurement provides the mass needed to calculate expected acceleration, and when you run the numbers, everything aligns. The 2.6-kilometer nucleus outgassing at the rates observed by spectroscopy produces exactly the acceleration seen in the trajectory. The physics checks out. But this size also has uncomfortable implications for planetary defense and our understanding of what's passing through our solar system undetected. If 3I/Atlas were inactive, if it were just a dark rock without any ice to sublimate and create a visible coma, we almost certainly would have missed it entirely. Its visual magnitude without the coma would be far too faint for most surveys to detect. Researchers now estimate that at any given time, there's likely at least one object the size of 3I/Atlas within 4.5 astronomical units of the Sun, roughly inside Jupiter's orbit. Most of them remain invisible because they're not outgassing. We only see the ones that happen to have enough ice and happen to pass close enough to the Sun to activate. This realization fundamentally changes how we think about the local solar neighborhood. We've gone from thinking interstellar visitors are rare to recognizing they're probably quite common. We just can't see most of them. The three confirmed interstellar objects, Oumuamua, Borisov, and Atlas, represent the tip of a much larger population. For every one we detect, many others slip through unnoticed. While Hubble measured the solid body and TESS captured the motion, the James Webb Space Telescope has been analyzing what 3I/Atlas is made of, and that's where the story gets genuinely puzzling. JWST's infrared spectrometers can identify molecules by their characteristic absorption and emission patterns at specific wavelengths. In mid-December and late December 2025, JWST observed the comet at distances between 2.2 and 2.5 astronomical units from the Sun. The spectra revealed water vapor, as expected for any comet. They also showed carbon dioxide and carbon monoxide, standard cometary volatiles, but then at 7.6 micrometers, a massive signal appeared that shouldn't be there. Methane. This wasn't a trace detection. The methane production rate reached 13.7% relative to water in the first set of observations and climbed to 27% in the second set. That means for every 4 water molecules escaping the comet, 1 methane molecule was escaping too. This is an enormous fraction, far higher than what we see in typical solar system comets. But the real mystery isn't the amount of methane, it's the timing. Methane is what chemists call a hypervolatile compound. It turns from solid ice directly into gas at extremely low temperatures, much lower than water or carbon dioxide. If methane ice exists on a comet's surface, it should be the very first thing to sublimate as the comet approaches the Sun. In fact, it should boil off long before the comet gets hot enough to release significant water or CO2. But that's not what happened with 3I/Atlas. When JWST first observed the comet back in August 2025, as it was still approaching perihelion, its closest point to the Sun, the spectra showed strong carbon dioxide and carbon monoxide signals. At that time, CO2 dominated the gas production, carrying about 87% of the total mass loss, while water contributed only 4%. Methane was completely absent. Not weak, not trace amounts, absent, zero detection. This made sense at the time. The comet appeared to be a relatively dry, carbon-rich object, unusual but not impossible. Then the comet passed perihelion on October 29, 2025, the moment of maximum solar heating. It began its journey back outward, cooling down as the distance from the Sun increased. By December, when JWST looked again, everything had changed. The carbon dioxide production had dropped dramatically. The water fraction had increased, and suddenly methane appeared in massive quantities. This sequence is backwards. You don't cook the most volatile ingredients last, you cook them first. Yet 3I/Atlas somehow managed to keep its methane locked away until after perihelion, only releasing it during the cooling phase when methane should have been long gone. This paradox forces us to reconsider the comet's structure. The most straightforward explanation is that the methane was never on the surface. It must have been buried deep inside the nucleus, protected by an outer crust that contained no methane at all. This implies a layered structure where the interior and exterior have completely different chemical compositions. The outer layers, exposed to the heating of interstellar space during the comet's billion-year journey between stars, might have been processed and depleted of hypervolatiles. Meanwhile, the interior remained pristine, preserving the original ice composition from whatever stellar system formed this object. As the comet approached the Sun, solar heating warmed the surface, vaporizing carbon dioxide and carbon monoxide from the outer crust, but the heat took time to penetrate inward. Only after perihelion, when weeks of solar exposure had conducted deep enough into the nucleus, did the buried methane ice finally reach sublimation temperature. Alternatively, thermal stress near perihelion might have cracked the surface, opening fissures that exposed fresh interior material directly to vacuum and sunlight. Either way, we're seeing a differentiated structure, not a uniform ball of ice and rock. But even this explanation has problems. Carbon monoxide is actually more volatile than methane. It sublimates at even lower temperatures. If the surface was warm enough to release CO back in August, it should have stripped away any near-surface methane at the same time. Yet CO appeared first, and methane appeared much later. This violates the expected volatility sequence. Something about 3I/Atlas's structure or composition is protecting the methane in a way that standard cometary models can't easily explain. One possibility is that the methane is trapped in clathrate structures, cage-like arrangements of water molecules that can lock methane inside at higher temperatures than pure methane ice would survive. Clathrates are known to exist in some solar system comets and are stable under different conditions than pure ices. If 3I/Atlas formed in an environment rich in clathrate formation, its methane might have been chemically bound in a form that only released when the clathrate structure itself broke down, which could happen at different temperatures and depths than simple ice sublimation. Another possibility is that the nucleus is a conglomerate, a mixture of different materials that accreted together rather than forming as a single object. Perhaps 3I/Atlas is the result of a collision between two bodies billions of years ago, one methane-rich and one methane-poor. As the combined object rotates and as thermal fractures open different regions, we're sampling first one component and then another, giving the appearance of strange timing when really we're just seeing heterogeneous composition. Whatever the explanation, the delayed methane release tells us something profound. This is chemistry that's been locked away and preserved since 3I/Atlas formed in its home stellar system. The methane hasn't been modified by billions of years of cosmic ray bombardment or exposure to the harsh interstellar environment. It's pristine material from another star's planet-forming disk, frozen in time and only now reacting to sunlight for perhaps the first time in its existence. When we analyze 3I/Atlas's methane, we're sampling the raw ingredients of a solar system that formed light years away, possibly with completely different conditions and chemistry than the nebula that birthed our own sun and planets. This is as close as we've come to touching another star system's history. The next chapter in this story unfolds on March 16, 2026. On that date, 3I/Atlas will pass within 53.6 million kilometers of Jupiter, close enough to enter Jupiter's gravitational sphere of influence, the region where the giant planet's gravity dominates over the Sun. This won't affect the comet's trajectory significantly. It's moving too fast for Jupiter to capture it, but it creates a rare scientific opportunity. NASA's Juno spacecraft, currently in extended mission orbiting Jupiter, will have a front-row seat. Juno wasn't designed to study comets any more than TESS was. Its instruments focus on Jupiter's magnetic field, radiation belts, and atmospheric composition. But those same instruments, particularly the magnetometer and plasma wave sensors, can detect interactions between the comet and the solar wind. If 3I/Atlas generates any kind of magnetic or plasma disturbance as it moves through space, Juno will measure it. The spacecraft's cameras will capture images from a perspective no Earth-based telescope can match. And while the encounter distance of 53 million kilometers is far too great for detailed surface imaging, it provides a valuable data point for understanding the comet's overall environment. This Jupiter flyby represents our last chance for close-range observations before 3I/Atlas fades beyond the reach of our instruments. After March, the comet will be too far and too faint for spectroscopy or detailed imaging. It will shrink to a point of light in astronomical catalogs, position and brightness recorded but no longer observable in detail. By 2027, it will likely be gone from our view entirely, headed back into interstellar space on a journey that will last millions of years before it encounters another star system. What we've learned from this visitor will shape how we approach the next one. The multi-wavelength, multi-instrument approach, combining TESS, Hubble, JWST, and now Juno, has demonstrated how much more we can extract from these brief encounters when we coordinate observations. Each telescope sees something different. TESS provides the time domain context and continuous monitoring. Hubble measures physical size and structure. JWST analyzes chemistry and composition. Juno will add plasma and magnetic field data. Together, they build a complete picture that no single observatory could achieve alone. The lesson for future interstellar visitor studies is clear. We need dedicated rapid response protocols, pre-arranged target of opportunity programs where multiple telescopes can quickly coordinate on newly discovered objects, and archival search capabilities to check whether we've seen the object before. We also need to accept that most of these visitors won't be dramatic or exotic. They'll be comets, probably quite similar to comets from our own Oort cloud in many ways. The exciting part isn't whether they're alien spacecraft, it's what their chemistry and behavior tell us about how planetary systems form around other stars. Right now, 3I/Atlas is magnitude 11.5 and fading fast. The rapid brightness decline after perihelion suggests the surface activity has largely shut down, either because volatile ices on the surface have been exhausted or because the nucleus has cooled enough that sublimation has effectively stopped. The brief methane outburst in December appears to have been a transient event, a window that opened and closed as deeply buried ice briefly reached sublimation temperature before being depleted. Within months, this object will go dark, its massive nucleus invisible against the background of space, joining the countless other interstellar wanderers we can no longer see. But the data remains. Terabytes of images, spectra, photometry, and measurements archived at NASA and ESA data centers, available to any researcher who wants to dig deeper. The methane paradox alone will fuel papers and modeling studies for years as scientists work out exactly what kind of structure and composition could produce the observed behavior. The size and mass measurements will refine models of how many interstellar objects pass through undetected. The TESS pre-discovery detection will inform future survey strategies, and the Juno encounter, when the data finally arrives, might reveal unexpected interactions or confirm that 3I/Atlas is exactly what it appears to be, a massive comet from another star system, chemically weird but fundamentally natural, now returning to the dark between the stars.